Okay, so let's get started. What is really important when you go to an exam? Because analog circuits is all about problem solving. So when you go to the exam, the things that you have to remember and solve there are circuit models. If you know the circuit models, then and there by applying KVL and KCL, you can solve circuits, right? So what are the circuit models you have to remember? Now, if you find any resistor in the circuit, resistor is not going to change its phase for DC and AC. So the resistance is R ohms, whether it is DC circuits or AC circuits. But if filter circuits are given, right, and you want to recognize the type of filter, then the circuit model you have to remember is capacitors. For DC, you can replace by open switch. For AC, short circuit. Inductor gives a complementary picture, short for DC, open for AC. So with this switch models, we have seen that in active filters, right? In active filters, with these switch positions, you can justify whether the filter is low pass, high pass, band pass, or band stop. Then comes the diode. If the diode is ideal, the circuit model is short circuit. Otherwise, you can replace the diode with an open with 0.7 volts if the examiner gives, right? Otherwise, you can replace the diode by short and start doing DC analysis. But when you replace this by short, 0.7 volts or short circuit, how do you know the diode is on? You have to prove that the current flowing through the diode is positive. If the current flowing through the diode is positive, then it is valid. But when you're applying small signal, then the diode for small signal is a resistor RD whose value is VT by capital I. So with this model, you can do small signal analysis problems. And 0.7 volts with this model, you can solve clippers, clampers, peak detectors, and so on. So for all these circuits, you have to just replace the diode by 0.7. And if you replace the diode by a resistor as an equivalent, VT by capital ID, then the signal has to be a small signal, right? So these are the different elements and their DC and AC picture. Then comes the BJT. Excuse me. So BJT, at least two elements are needed. Suppose if BJT is given with some DC, then what is the model? If BJT is a simple diode, we have seen, you have to just take 0.7. So you can take 0.7 and solve. But if you don't want the BJT there, then you can put this circuit as an equivalent. 0.7 volts between base and emitter, and you can solve. Or you can just take 0.7, that is better, right? And what is IC? At the output, the IC, mostly BJT problems will have emitter resistors. So IC is going to be beta by beta plus 1 times of I. You will take IC as beta by beta plus 1 times of I, right? So this is the model we are using for BJT. So this IC is beta by beta plus 1 times of I. If there is no emitter resistor, IC can be B-type. IC can be B-type. So this is for the DC picture. AC picture, the diode for small signal, we have seen it can do times of I, right? So this is the model we are using for BJT. So this IC is beta by beta plus 1 times of I. If there is no emitter resistor, IC can be B-type. IC can be B-type. So this is for the DC picture. AC picture, the diode for small signal, we have seen a resistor. So because this is a diode here at the input side, you have to put a resistor here. So what is the resistance? R5. This will be GMVB and VB. So this is the model that AC model neglecting early effects. But if you consider early effects, then you have to include another resistor here. So with this model, by applying Kirchhoff's laws, you can solve BJT in AC analysis. So last we are left with two devices. One is the MOSFET, the other one is op-amp. So if you have these models in your hand, by looking at that circuit, you can replace the device with this equivalent model. And by Kirchhoff's law, KVL and KCL, you can solve circuits, right? So in analog, there is nothing great to remember before going to exam. It's just the equivalent models. And the moment you find a problem, so then and there you can solve, right? So what about MOSFET? MOSFET, as you know, has 3 terminals: gate, source, and drain. And it's lucky that the gate current is 0, so MOSFET draws no current here. Between gate and source, you have voltage, but you don't have any current. IG is 0. So MOSFET draws no current. But what is ID? What is ID in MOSFET? Whenever you want to solve MOSFET problem, we have seen that ID was always K times of VGS minus VT whole square by 2. So this is the formula you have to remember, right? When the moment you find a MOSFET problem, just start with K times of VGS minus VT whole square by 2 is ID. And from there, by substituting VGS, you can get I, right? So this is simple. MOSFET is extremely simple when compared with BJT. And not to be forgotten, what is this K? This K is mu Cox W by L. This K is mu Cox W by L. So what is the AC model of the MOSFET? MOSFET draws no current. So it is VGS here. And this is GM VGS in parallel with R. Now, what is this GM and R0 values in BJT and MOSFET? We have to know. So this R pi is nothing but beta by GM. And GM is nothing but IC by V. MOSFET draws no current. So it is VGS here. And this is GM VGS in parallel with R. Now, what is this GM and R0 values in BJT and MOSFET? We have to know. So this R pi is nothing but beta by GM. And GM is nothing but IC by V. And R0 is early voltage by IC. So these are the values for BJT. So for MOSFET, what are these values? GM is going to be, and R0 is early voltage by IC. So these are the values for BJT. So for MOSFET, what are these values? GM is going to be K times of VGS minus VT. This is VGS DC. The AC parameter is dependent on DC. And R0 is equal to early voltage by IC. Sometimes he gives 1 by ohm, which is lambda. So sometimes if he gives lambda conductance, then you are lucky. You can simply take R0 equal to 1 by lambda. R0 equal to 1 by lambda. If he gives lambda, then you are lucky. Directly R0 equal to 1 by lambda you can take. Otherwise, early voltage if he gives, you have to divide it by ID. ID here, this is not IC. But usually lambda will be given, so 1 by lambda you can take. So this model is the AC model for MOSFET. So these models you have to have in mind. The moment you find a problem, you replace the device with the equivalent model. This is number stage control voltage source. So this is an op-amp. If you want an equivalent model, then you can have RID here. This is plus and minus terminal. If the examiner says ideal op-amp, then remember op-amp draws no current. So RID is infinite, this is VD, and R0 is 0. RID is infinite and R0 is 0, right? AV. So this model you can use. Why the input resistance is high for op-amp? Purna Satya Srinivas. See, op-amp's input resistance is high because the op-amp's first stage is a differential amplifier with a cascode connection. So these terminals are actually base terminals of the transistor. So definitely the first stage is a differential amplifier. You want high input impedance so that it can behave as a VCVS, right? So that's how it has been constructed inside, right? But because op-amp is having high input resistance and low output resistance, that is when the op-amp is used as a VCVS. Let me tell you here. Yeah, suppose you have an amplifier. The amplifier, type of amplifier is always decided by its Rin and R0. So if Rin is high, the amplifier is voltage controlled amplifier. If R0 is low, it is current controlled. If Rin is low, it is current controlled. If R0 is low, it is a voltage source. If R0 is high, it is a current source. So if the manufacturer himself is giving you an op amp, which is a VCVS, it is his duty to VCVS. That means he has to maintain Rin high and R0. He has to maintain Rin high and R0 low while manufacturing. And to do so, he has a differential amplifier with a cascode connection as the first stage. Its input resistance is around 1 gigaohm, right? Or in tens of gigaohms. The output resistance is less than an ohm, right? Or almost 1 ohm like that. So if suppose an op amp was a current amplifier, if op amp is a current amplifier, then its input resistance would have been low and output resistance would have been high. If suppose instead of an op amp, you buy an OTA in the market, an OTA is an operational transconductance amplifier. So if you buy an OTA, then it is a voltage controlled current source, transconductance. So your Rin should be high and R0 also should be high. If it is a trans resistance amplifier, then Rin is low and R0 is low. Yeah. See, this way we can have you can ask doubts. This is better. That way I know what I should teach. Otherwise, okay, so an amplifier is solely decided on the basis of its input and output resistance. Yes. What sort of bits? If you see old gate problems for 1 mark, these days there are no theory bits. Only problems are there. But when we used to write gate exam, they used to ask why IOP is 0? Why the current in an op amp is 0? IOP is 0 only when RID is infinite. If the input resistance of op amp is very high, then op amp draws no current. Op amp is going to draw no current. And why V0 is AVD? In op amp, we always say V0 is AVD, or we say V0 is A times of V1 minus V. This is only when V0 will be AVD only when R0 is 0. V0 is AVD only when R0 is 0. Yeah. So please stress what is important for gate exam. That's what I'm telling you. For gate exam, you will be given problems. right? You'll be given problems and you have to solve problems then and there. For that, the best tool for you is these 7 things. These are the only things, in my opinion, are important when we go for an exam, right? And apart from that, I have given you few shortcuts which I wanted to highlight. What is the shortcut that I have given you is, if you find a BJT, if you want to avoid small signal model, I told you a BJT has R pi at the base terminal. It has alpha by GM at the emitter terminal, and it has R naught at the collector. So this logic will save a lot of time. Otherwise, you can do again by small signal model, right? The input resistance of to base is R pi, emitter is alpha by GM, collector is alpha. And you have to remember these multiplication factors if you want to save time. So what is the input resistance here? If you see through base terminal, it is R pi plus this current gets multiplied by 1 plus beta times of R. Right? If you have a resistor at emitter and you are seeing through base, then it is alpha by GM plus R divided by 1 plus beta. R divided by 1 plus beta. Right? And generally early effect problems are not given in exam. If examiner gives a early effect problem, which this we have not seen in GATE exam, but okay, if you want to calculate the resistance at collector when there's a resistor here, then the resistance is going to be R naught plus 1 plus GM R naught into this R is going to come in parallel with R pi. So this we have not seen in GATE, but okay. So this way you can avoid the small signal model. So these models are very, very helpful because see, in my opinion, any subject 4 bits they will ask. So hardly 4 bits, 4 or 5 bits, is it not? 8 to 9 marks you can get. So the topics can be divided as op-amp, BJT, MOSFET, diode. MOSFET and diode. In BJT, if he gives DC analysis, then he will not give AC analysis. If he gives AC analysis, he will not give DC. But in MOSFET, you can expect one problem from DC and one problem from AC. BJT, you can expect, op-amp, you can expect 2 questions. Both the questions can be from negative feedback, we cannot say, right? So it's mostly from negative feedback, sometimes Schmitt-Trigger. So these are the 2 areas you should focus: negative feedback circuits and Schmitt-Trigger. Negative feedback circuits and Schmitt-Trigger. Mostly from negative feedback, sometimes Schmitt-Trigger. So these are the 2 areas. Yeah, Janvi. Okay, Janvi. Yeah, it's the same for triple. Yes. So BJT, you can expect 1 question on DC circuits. Diode, I think you can handle. You just replace the diode by short or 0.7, and you can have circuits like peak detector or clamper. Right. So if you can broadly think in those terms, then revision will be easy for you, is it not? Otherwise, looking at the whole subject, it's cumbersome, right? So this is simple. Solve diode problems for confidence. MOSFET, DC and AC circuits. Op-amp negative feedback, you try to solve. Few with capacitor, without capacitor. Schmitt-Trigger, you see, that's it, right? 1 or 2 problems on DC analysis of BJT. Okay. Yeah, I was trying to say that these things, if you remember, then it is going to save time. So similarly, for MOSFET, the resistance reflection rule, the gate current is 0, so the input resistance here is infinite. Here it is going to be alpha is 1 in MOSFET as compared with BJT. Alpha is 1 and beta is infinite. So whatever we have done here, if you put alpha 1 and beta infinite, you are going to get the same answer. So the MOSFET just converts to BJT. So here you are going to have 1 by GM, and this is R naught. And MOSFET is extremely simple, because even if you have multiple MOSFETs, it's quite easy for you to solve, because MOSFET has a single current. So this is the only thing you have to remember. What is the output resistance? If suppose there are amplifiers like cascode and all that, then R naught is going to be R naught plus 1 plus GM R naught into R. So only this you can remember. This R can be another MOSFET. Say for example, a gate problem was given where two MOSFETs were there. So this guy has R01 and this guy has R, right? So what is the output resistance? He has asked. So it is R naught plus, if you remember this, it is R naught plus 1 plus GM R naught into R. In the place of R, you have R02. This is the answer. So this is given for 2 marks. So it is R01 plus R02 plus GM1 R01 R02. So out of this, GM1 R01 R02 is the answer. So this way, things are simple, right? Non-idealities, slew rate and CMRR problems you see, right? Generally non-idealities. Just see slew rate and CMRR problems are also off late, they are not asking. But that's the only non-ideality where you can focus, right? Because see, the examiner, just imagine, if you are an examiner, you have a big subject. Now, which topics will you focus? The topics which have some weight, is it not? So, op-amp negative feedback, yes, pakka question. MOSFET DC analysis, AC, pakka question. So, 6 marks are over there. 8 marks means another 2. Diode you will give, finished. Somewhere at the corner, something that is not at all important and that will not have any physical implication. Then those kind of things he will not ask. See, that is why I've already told you. When you are preparing for an entrance exam, what is more important is you should know what you should not study, right? So you should avoid a lot of things which are not important, in the final days. And you should focus. You should be very focused. These are the areas I'm going to revise, and the whole subject you can make it very small, right? Like how I have divided 4 parts. Like every subject you have to think in those terms. So specifically going in depth into what is an offset and all that. What is there? Non-idealities means that is again KVL and KCL, right? He himself will say op-amp is drawing current. So you take some current there, apply Kirchhoff's law, you'll get the answer, right? But there is specifically there is no need for you to remember, right? Yeah. Oscillators generally they are not asking, because oscillator problems will become big because you have an amplifier and so you need a second order system. Right? You need a second order system. So this is the reason probably last 10 years they have not asked, right? One standard Wien-Bridge circuit, direct to formula substitution, they have asked for triple students. But generally, if you see, oscillator problems are generally for 10 marks. So what you can focus on is, if you are given a new oscillator, which you have not seen, then you should focus on the loop gain, that's all. What is loop gain? You start at one point, come back to the same point, and multiply all the gains in the loop, and that is going to give you the frequency of oscillation. So if he has given some circuit, is it not, which you have not seen, then you can do like that. Okay? Yeah. Timers are not important. No, there is no timers. Yeah. Okay then. Chalo. So this is about what you have to remember for exam. We can take Yeah, there's some problem with the internet. Can you see the screen now? Is my voice audible? Can you see the screen? Yeah. Yeah, thank you. Yeah, so this is what I was trying to tell you, that in the last moment, your short notes, whatever you have prepared, that is going to really help you. And try to solve problems on specific areas, so that you can recollect things much easily, right? Yeah, and one last thing I forgot. I was asking you to remember a few things and then solve some problems on differential amplifier and correct. Sure, what is there we can solve? Yeah, one last thing to remember, I told you, is whenever you have an ungrounded resistor between input and output, Vx and Vy, then this can be split into two grounded resistors. One from this node Vx to ground, and this is from Vy to ground. So this is called what theorem? Miller's theorem. So this is a formula which you have to remember. It will save time. Otherwise, you can do by Kirchhoff's laws. So what is R1? R1 is equal to R by 1 minus output voltage by input voltage, Vy by Vx. And R2 is going to be R by 1 minus 1 by Vy by Vx. So this is something you have to remember, right? So if you remember this formula, then we can apply it everywhere. Suppose you have an op amp. In op amp, if you find a resistor R here or a capacitor, this is V2 and this is V0. Then you can split this in this fashion. From V2 to ground, you can have R1. From V0 to ground, you can have R2. And what is R1? R1 is going to be R by 1 minus output voltage by input voltage. And R2 is going to be R by 1 minus 1 by output voltage by input voltage. Now, what is the relationship between output and input? V0 is A times of V1 minus V2. So, V1 for an op amp is 0. So, it is minus A2. So, V0 by V2 is going to be minus A2. So once you know that this is minus A, you can just substitute here. R0 by 1 plus A. Then R2 is going to be R by 1 plus 1 by A. So this is according to what theorem? Miller's theorem. So this is very, very important. And the division can become multiplication if you have a capacitor. If you have a capacitor, then the division can become multiplication. The division can become multiplication. So it is minus A2. So V0 by V2 is going to be minus A. So once you know that this is minus A, you can just substitute here. R0 by 1 plus A. Then R2 is going to be R by 1 plus 1 by A. So this is according to what theorem? Miller's theorem. So this is very, very important. And the division can become multiplication if you have a capacitor. If you have a capacitor, then the division can become multiplication. The division can become multiplication. So if there is a capacitor between input and output, this is split into C1 and C2, where C1 is going to be C multiplied by 1 plus A, if A is the gain, and C2 is going to be C multiplied by 1 plus 1 by A, which is approximately C. Or you can use the formula. What is C1 is going to be C multiplied by 1 minus output voltage by input voltage. This is the formula. What is A? A is the gain of the amplifier. In an op-amp, this is the non-inverting voltage V1, this is V2, this is V0 and A. So op-amp general expression is V0 is A times of V1 minus V2. Op-amp is A times of V1 minus V2, right? So where A is the gain of the amplifier. What is A? A is going to be the gain of the amplifier, right? The open loop gain. So in negative feedback, what happens in negative feedback? In negative feedback, whenever you want to solve negative feedback problems, if you are given some voltage, then you should not forget that in negative feedback, whenever you want to solve, you have to take two assumptions, right? One is the voltage at non-inverting is voltage at inverting. Two, op-amp draws no current. Op-amp draws no current. So if this is Vin, and this current is in. And now it becomes a network. You can apply KCL, entering current equal to leaving. So V0 minus Vin by R2 is 0 plus Vin by R2. So from here, you get V0 is 1 plus R2 by R2 times of V. So whenever you find an op-amp with negative feedback, you can apply virtual short. So virtual short is valid only when A is infinite. A is infinite because V0 is A times of V1 minus V2. So V1 minus V2 is V0 by A. If A is infinite, then only you have to apply V1 equal to V2. So V1 minus V2 is 0. So please don't apply virtual short if the gain is finite, right? And then you can solve. After that, it's just Kirchhoff's laws. Yeah, I was talking about the Miller's theorem. So the Miller application can be given to BJT and MOSFET. So if you have a resistor or a capacitor here, we are talking about a capacitor. Say this is a VB and this is VC. So now this capacitor can be split into two capacitors, one from VB to ground, another from VC to ground. And what is the relationship? C1 is going to be C multiplied by 1 minus VC by VB. Output voltage by input voltage. And C2 is going to be C multiplied by 1 minus 1 by output voltage by input voltage. So this is how you can apply Miller's theorem for all the devices. So similarly, you can apply for MOSFET also. So you have a MOSFET and there is a resistor here, R. This is VD, this is VG. You can split it into here R1 and R2. So what is R1? R1 is going to be R by 1 minus output voltage by input voltage. And R2 is going to be R by 1 minus 1 by output voltage by input voltage. So this way, you can apply Miller's theorem for all these devices. Yeah. Now students are asking, they want to take one problem on a certain topic and do it. I think that is better, right? So we can take, so that we can cover. Because some students are asking for region of operation and Miller's and all that. So it's better we take one problem on each topic and then we can cover so that you also will know, is it not? It will be a revision kind of a thing because the main aim of today's class is revision only. So we will try to revise the concepts through problem solving. Let us revise the concepts through problem solving. That is better. So we'll do that. Grounded resistor can be replaced by two grounded capacitors and two grounded inductors. It is not only a BJT. See, you can apply Miller's theorem here also. Suppose I am having a BJT here. There is another BJT. There is another BJT here. And somebody has connected a capacitor between input and output here. So you have to first name this as Vx, this as Vy. So Miller said that if you have an ungrounded capacitor between 2 points, it has to be replaced by two grounded capacitors, one from the same point to ground, another from the same point to ground. So you think in those terms. It is not that, because students have a wrong notion that we have to apply Miller's theorem only to this specific case. No. Miller said if any capacitor is ungrounded, you can replace it by two grounded capacitors. That's the main intention. So it is connected here. So what is C1? This C1 is going to be this C multiplied by 1 minus where this capacitor is connected. Its left leg is connected here, right leg is connected here. So you have to write 1 minus Vy by Vx and C into 1 minus 1 by Vy by Vx. Are you getting? Wherever there is a capacitor which is ungrounded, you can replace it by two grounded capacitors. Similarly, wherever there is a resistor ungrounded here, it can be replaced by two grounded resistors, right? But remember, the answer is quicker, but it is not accurate. You will not get accurate answers with Miller's theorem. That is why Miller's theorem is also called Miller's approximation. Miller's theorem is also called Miller's approximation. Okay. So now we'll start solving problems. So this is exactly what I wanted to tell you. These are the only things you have to remember for exam. These are the only things you have to remember for exam. So let me repeat. One is the models of all the devices. All the devices, these specific models. And of course, these are shortcuts. If you want to save time, avoiding the small signal model. And Miller's theorem. These are the only things you have to remember. Right? There is no other thing. So let's solve some problems. So that way we can move on. Right? The time constant. The time constant tau. You are asked to calculate the time constant tau. So we have resistors and capacitors and an op amp here. And this op amp has some gain. Say it has 10 gain. So how are we going to solve this problem? This op amp has some gain. Yeah, you want my video also? See, because I'm not well, so I'm not really comfortable, so I'm doing like this, so I just switched off my video. Is it okay if I switch off my video? Because my cold is unbearable cold. Is it okay if I switch off my video? Because I keep doing this and I'm not comfortable. That's it. Okay, thank you. Thank you. So let's solve this problem. So we have V in here, R here, R here, C here. But there are no resistors at output side. So I told you this capacitor can be split into, suppose this is V2, V0, V2, V0. It has to be split into two capacitors, C1 and C2. Whenever you are calculating Thevenin's equivalent, Thevenin's resistance, the voltage sources should be shorted. When you short, these two resistors will come in parallel. So finally, you have R parallel with R. And here you have C and C1 in parallel. So tau is nothing but R equivalent into C equivalent. Tau is nothing but R equivalent into C equivalent. There is isolation between C1 and C2. C1 is at the input side and C2 is at the output side. There are no resistors in output. If there are resistors, then we can say tau equal to RC. So it's something like, this capacitor is in Hyderabad and this capacitor is in Delhi. So the tau is a function of only C1 but not C2. So what is R equivalent? R equivalent is going to be R by 2. And C equivalent is going to be, if two capacitors are in parallel, what is the overall capacitance? It has to be addition. The overall capacitance has to be addition. The overall capacitance has to be addition, right? That's it. So what is tau? Tau is this product. But what is C1? I told you. C1 is going to be C multiplied by 1 minus V naught by V. So it's 10. Minus of minus 10. It is 11C. So V naught by V2 is going to be minus 10. V naught by V2 is going to be minus 10. So it is C minus of minus 10. It is 11C. So let me put C plus 11C. It is going to be 12C. It is going to be 12C. So what is tau finally? Tau is going to be R equivalent into C equivalent. It is R by 2 into 12C. So it is 6RC. 6 Venkatesh, very good. Right? So 6RC. It is going to be 6RC. Here, we cannot consider C2. Even if you consider C2, yes, suppose you want to consider C2. So if I consider C2, I have to say tau 2 equal to C2 into the output resistance of op amp is 0, ideally. So it becomes 0. So there are no resistors here. A good op amp output resistance will be very low. So nothing is given because we are the ones who split it into C1 and C2. And my resistors are at input side. When my resistors are at input side, only C1 is going to affect because tau is the equivalent resistance seen by capacitance and the equivalent capacitance seen by the resistor. So these two fellows should be like brothers, in the same network. Then only we can multiply them. So this fellow is isolated. So this C2 is not going to come into picture. Okay? Yeah. Now, when can you apply virtual ground? Virtual ground is applied when the examiner says op amp is what? Ideal. Op amp is ideal. Right? So, do not apply virtual ground if there is no feedback. Suppose there is no feedback, you should not apply. So, because V0 is A times of V1 minus V2. This gain is very large. It is almost infinite. So, if no feedback is given, you are given V1 and V2, then what is V0? Say this is say plus 10 and minus 10. So this is a simple comparator. An op amp, you should not apply virtual ground in open loop. Open loop. So in open loop, V1 greater than V2. If V1 is greater than V2, suppose this gain is infinite. This gain is infinite. V1 is greater than V2. Then V0 is going to be A into some positive value. Positive value. So this is going to be plus infinity because A is infinite. It is infinite times of V1 minus V2. So plus infinity then minus infinity until the examiner mentions. If the examiner does not mention, you cannot assume it is 5 ohm, 10 ohm like that, right? A good op amp, you should always be optimistic. The problem is given, it is a good op amp, right? It's not saturating. Its input resistance is infinite. Its output resistance is 0. That is how you have to feel. Because he himself says an ideal op amp is, if he specifically mentions some resistance, then it's okay. But generally we don't. He will always focus on input side, not at the output side, right? But if he gives input resistance, output resistance, then you can use the model which I given. For that model, you can use, right? In the previous problem, if the output resistance is given, then what will be the time call? You have to add tau 1. See here, forget about what you call output resistance. If a load is given, I'll make one load here, R. So if a load is given, then you will have another R here. R here. Then tau 2 is going to be R into C2. Tau 2 is going to be what? R into C2. Then the total tau is going to be tau 1 plus tau. Remember, please, the total tau, the total delay offered by the system is the delay of individual poles. Each pole, that means each capacitor is giving some signal delay. The signal which is traveling from source to destination is having 2 poles. So the total tau is going to be tau 1 plus tau 2 you have to do. Please remember that. Right? Tau 1 plus tau. Okay. Yeah. So this is about a simple comparison. Now, Let us take a problem with negative feedback, right? So you can have some transistor circuit where the feedback is there. Whenever there is negative feedback, you can always apply virtual short. You can always apply virtual short. So some voltage, 5 volt, something you take 5 volt, 3 volt, some random voltage I am taking. So find V naught. Yeah, Jan. Find V naught. So if the op amp gain is very high and it is ideal, and there is what feedback? Negative feedback. You can apply virtual short. What is virtual short? The voltage at non-inverting is equal to voltage at inverting. The voltage at non-inverting is equal to voltage at inverting. And op amp draws no current. Op amp draws no current. Op amp draws no current. Then the good thing is, if you take some current I here, or I1 and I2 and I3, you will realize that because this current is 0, this I1, I2, I3, all are same. All are same because op amp draws no current. This is I, this is also I. So what is I? I is going to be 3 minus 5 by 1. It is minus 2 milliampere. And now you can take a loop here, KVL. So what is KVL? See, this is why op amps are so easy, because once you apply virtual ground, it's a problem of resistors. It is a simple problem of resistors, right? You can just remove op amp from there, the resistors, and then calculate. Because once you apply virtual short, voltage at non-inverting is voltage at inverting. You don't need an op amp anymore to calculate. So you can tell me what is the KVL here. It is I into 3K plus I into 1K plus I into 2K plus V naught is 0. So V naught is going to be minus I into 6K. Substitute I equal to minus 2. Substitute I equal to minus 2. So 3, 4, 5, 6. And the current here is 2. So how many volt is this? V naught is minus I, so it's going to be 12 volts. Good. 3, 4, 5, 6, 6 2s are 12, right? Six twos are 12. So find V naught. Find V naught. Suppose this gain is infinite and this gain is 10. The gain here is infinite and the gain here is 10. So now you understand the difference between virtual ground and this. So you can take some node Vx here, Vx. So for this circuit, you can apply virtual ground, but for this circuit, you cannot apply virtual because the gain is less. So let us solve this circuit, right? So voltage at non-inverting is equal to voltage at inverting, and you can have entering current equal to leave. Or if you remember the non-inverting amplifier formula, it is okay. So Vx minus 3 by 2k equal to 0 plus 3 minus 0 by 1. So your Vx is going to be 1 plus 2k by 1k times of 3. So this Vx is going to be how many volt? 9 volt. 1 plus 2k by 1k times of 3. 3 3s are 9. Right? Now just correct me whenever I do some mistakes in simple calculation. Right? sometimes I bound to do well, at least when you have too much cold, right? So sometimes I might write 3 3s is 6 like that. So that way I can know whether you are attentive in the class or not, right? So 3 3s is going to be 9. Now for this problem, you are not allowed to apply virtual. So let me draw this here separately for you. This is 10. Here you have a 9 volt and this is 2K V0. So for this problem, you have to use the formula V0 is A times of V1 minus V2. V1 equal to V2 only when A is infinite. V1 equal to V2 only when A is infinite. So let us substitute 10 here. V1 is 0 volt, V1, this is V2. So it is 0 and V2. So your V0 is going to be minus 10 V2 minus 10 V2. Now you can see here we have applied a virtual ground. Both are same. Now the same KCL you can apply here also. Op-amp draws no current. V0 minus V2 by 2K equal to 0 plus V2 minus 9 by 1. So this is equation 2. In equation 1, you have V0 and V2. In equation 2, you have V0 and V2. So from 1 and 2, you can find V0. From 1 and 2, you can find the V0. Definitely, this answer should be less than minus 80, right? Less than. Venkatesh says it's around minus 13.5. Says minus 13.5. So let me take that. So I can accept this answer because it's less than 80, right? But Dhanashree says minus 15 also. So I don't know which one, but it should not be 18 because minus R2 by R1 times of 9 is 18. So the answer should be less than 18. The answer should be less than 18. So your V2 is V0 by 10. So it should be 1.35 volt will be the error between the two. 1.35 into 10 is going to be 13.5. So you're saying V2 is 1.35. So just check. So please apply virtual ground only for an amplifier which has infinite gain and negative feedback. Do not apply virtual ground if it is finite and there is negative feedback. You have to do V0 is A times of V1 minus V2. 13.84, Abdul says. So, okay, so it's close to 13, right? It's close to 13. It has to be less than what you call minus 18. But Abdul, it is a positive voltage.